If you've wondered how schools and universities are starting to detect AI use in assignments and things like that, for a university course of mine, I actually recently had to look into a paper that details exactly the methods that they're using to try and do this. I actually have to give a seminar presentation that's assessed on it tomorrow, so I thought I'd make this video. We'll go through the paper, I'll share something really cool with you, and it'll give me good practice for the presentation. Also, my seminar partner for this particular one, it's a duo. I'm actually going to ask her out after the seminar presentation, so make sure you wish me luck for that. Let's get into it. Okay, so here's the paper in question. It's titled Deepfake Text Detection Limitations and Opportunities. It's quite lengthy and it's very detailed. There are lots of tables, lots of graphs, but we're going to go through and break down the very most important things so you guys can sort of get a higher level understanding of how they're actually detecting AI use in assignments. So essentially, their first thing here on this introduction is sort of explaining why you'd even bother detecting AI text in the first place. There's actually many, many reasons for that. Assignment cheating is not just the only one. There's like, people are able to generate news articles about whatever they want in the style of authors that they want, they can choose from. It's going to be a big problem there. Like you've got phishing scams where, think of how many people today, like in this day and age, fall for the really generic, like you've won $1 million phishing scams. If you can introduce AI to that, it's going to be grim for grandmas everywhere across the world. It's not looking good. There's lots of more reasons beyond just like cheating in assignments that you'd want to like try and detect AI generated text. So that's really the point of their introduction there. And they kind of go over a couple of methodologies and things. Essentially, the long and short of it is they have down here some defense models. So they're actually going to use AI to detect AI, which is pretty interesting, right? You can see one of these is actually based on a GPT-based model, which is like ChatGPT. It's GPT-2. I think GPT is up to GPT-4 by now, but anyway, they've got other language models as well. If you didn't know, ChatGPT is not the only large language model that can generate text and things like that. But essentially, what they're going to be doing in this paper is really interesting. They're going to build a binary classification layer on top of these large language models. Essentially, what that means is they're going to build into the model. So these models are capable of generating text, but on top of that, they're going to look at their pre-trained data set and build a classification layer on top of it. So if you can feed it AI generated text, it'll say this is AI or this is not. That's what a binary classifier is. It's an AI model that just goes, yep, this is this, or no, this is not. So in terms of the datasets that they use to train those models that we were just looking at before, they've got a couple of different ones. So to train these ones, they use these real and synthetic datasets. So essentially, this one here is web text, right? This is a real dataset. It's known as an open domain dataset. So that means that the text that comprises this dataset is not limited to one particular genre or style. So for example, it might incorporate news stories, short stories, encyclopedia pages, things like that. Whereas this dataset down here used on these defense models is called real news. It's a very inventive name. As you can probably guess, it's for news articles that are actually legitimate, right? So these models down here are trained to detect fake news, basically. And these ones up here should be like open domain, so generalizable to any text that they get. So that's assignments, things like that. Now, of course, if you want to train a binary classifier, you've got to have something to compare it with. So for this synthetic data set right here, what they're doing is they're getting text generated by a GPT-2 large model, a GPT-2 XL model, and one called Grover. So Grover, you can actually train it on itself, which is pretty interesting. But Grover is basically just for generating news articles. So this is their test and train datasets. They're going to train it on web text and real news for real ones, depending on the model. And then they're going to grab a whole lot of synthetic generated text and feed it that. So it can basically train itself on, hey, this is real, this is fake. And we're going to have a look at how well this does later on. So in terms of like the datasets that they use to, and I'll blow this up for you, but the datasets that they're using to test the outcomes of this, of course, you want it to be different from just the ones that it was trained on, because otherwise you don't know how useful your model is. So they're using these datasets right here to do sort of an in the wild, they call it, dataset, like test. So they've got 4 synthetic datasets here. These 2 at the top are news ones. So this will be more applicable to these ones down here. So Grover, Fast, and Roberta Defense. And these 2 down here, Kafka and RedditBot, are open domain. So they should be applicable for all of them. Now, RedditBot's are actually a very interesting case because the way that they got that dataset, back in 2020 or so, there was a GPT-3 based bot called, I think it was you slash the gentle meter or something like that. But essentially, it masqueraded as a real user on Reddit for a couple of months, and they grabbed all of its comments and the replies to the comments, and bing, bada, boom, slap that in. You've got a dataset to train AI on. Yeah, a dataset trained on Reddit comments. Yikes! But anyway, it is what it is. That these are the ones that they're going to be using, and we can have a look at their performance numbers for these. Like, just to give you an example for what these tables actually mean, because they've got a lot of the tables with a lot of numbers. The metrics that they're actually like considering here, and I'll flash the formulas up on screen. But when you've got a binary classifier, you really look at three main metrics. The first one is precision. So precision is essentially the number of true positives that you got. So that's out of all the ones you flagged as this is correct, divided by that same number plus the number of false positives. So if you think about it, it's a measure of how accurate you were. So out of all of the positives you flagged, how many of those were correct? Recall is very similar. It's the number of true positives you got again on the numerator, divided by the number of true positives plus the number of false negatives you got. So that's essentially out of the entire set of positive answers, how many of those did you get correctly versus how many of those did you flag negatively? The F1 score is kind of a combination between these two. It's actually the harmonic mean of the two. Yeah, I know. Just a higher F1 score is better for the purposes of this video. So coming back up here, you can actually see they perform pretty well on their own test and train dataset. So this is the original one here. And you can see that the performance of these models, I meant to only highlight this part over here. But you can see it's actually pretty good. So the F1 scores, like the lowest one here is 80% basically. And the precision and recall scores are also pretty good. So let's see how this compares when we take it outside of its original training dataset and bring it into the real world. Here, as you can see, they perform pretty abysmally when brought into the real world. So you can see these are the delta F1. So basically before, like the baseline F1 versus what it gets now, you can see these are like 20s. This one's a 65. It's not terrible. This one got a minus 99%. Like, it's pretty shocking across the board, except the news ones. The news ones actually still remained really, really well after the, after bringing it into the wild. It's just the open domain ones that really suffered. And I suppose you could hypothesize that because the open domain ones have such a large variety of text that they need to detect as AI generated, it's a lot more difficult. Whereas the news ones, news articles are generally all written in the same style, so it's probably more transferable outside the original data set. So now we're going to have a look at how they actually made these models and what they're sort of planning to do to sort of bring these numbers back up to a good number. A really interesting one I want to highlight over here are these GLTR ones, because essentially they exploit one of the fundamental ways that large language models work. And that is essentially when the large language model is deciding what token comes next. Like, you're trying to generate a paragraph, right? The large language model has to decide what comes next in that sentence. And it does this based on probability. And these two ones here, GLTR, BERT, and GPT-2, both exploit this. So essentially, what they do is they analyze the likelihood of the tokens in the sequence as determined by the language model. So let's say that I'm looking at ChatGPT, for instance, and ChatGPT likes to use some words more than others, and you can generalize that across lots of different text. Well, if you've got a entire like assignment, right, where these words pop up at a frequency much higher than what you'd expect from an actual human, that's a dead giveaway that that's by AI. So these two models here sort of, they exploit that property of large language models where you can sort of take a look at the probabilities, and if they don't stack up, then you can say, okay, this is AI. I want to turn your attention to another really interesting model. This one is called FAST. So FAST works a bit differently. Instead of exploiting the probabilistic nature of large language models, it looks into the semantic or factual structure of the text, as they say. So for example, if I'm writing my short story and the main character is called Greg, and then suddenly in the following paragraph, the main character is called Bob, that's an inconsistency. And that's a really dumb example, but large language models make this mistake all the time. For example, if you ask for a travel itinerary for Spain, for instance, it could spit out things from a completely different country. Like, it'll start off being about Spain, and then it'll mention a city that's actually not in Spain and things like this. So FAST can actually have a look at location, people, objects across sentences and sort of build, as they say, I think it's a graph-based network. of all of the things in the text to look at inconsistencies, which is really interesting. So they train these models, right? These ones over here work based on exploiting probabilities. This one is basically trained on a massive data set of both synthetic articles being itself generated and real articles, and it just tries to classify the two. This one builds a cheeky little graph. This one over here was actually cooked up by the researchers. It's pretty interesting. But essentially, these open domain models perform pretty poorly in the wild. So we're going to have a look at how they go about fixing that. And the answer is actually with fine tuning. So fine tuning is essentially the process of if you have a pre-trained language model or any AI model for that matter, and you want to sort of expand its functionality to a new domain that it hasn't seen before, but you don't want to retrain the entire model. You can take a more focused, smaller data set and retrain based on that. And instead of having to train the model from the ground up, you can see whether or not those sort of skills or the accuracy transfers to the new domain. So they did a very interesting thing here, which is they did different numbers of samples for the fine tuning. So from AI Writer, for instance, you would take 10 samples from this and fine tune. They used BERT Defense and Grover. So we're going to look into this because it's very interesting because it comes with a scenario of like, if you think about what the attacker has up their sleeve, right? New models, new language models come off the presses all the time. If you've got a hot new model that's straight up and you're using it to cheat in an assignment, the defender being like, turn it in or something like that, they want to have the least amount of lag time possible before when that new model comes out and when they can start detecting and catching cheaters. So if you think about it, collecting that data set will actually be kind of annoying because the text, like the AI text from the new model, might be so realistic, it takes a lot of time to sort all of the information. So really it's an optimization problem, like how little fine tuning can you get away with? And 10 actually works pretty well. Like you can see here, Grover after 10 goes to 90 and 86.5. It's not much of a change because Grover was already pretty good performing, but it's nice. But BERT Defense, which was an open domain model, actually had a really, really good impact with this. So you can see it goes from a 28.8% F1 score to 68.9. And at 50, basically the lowest goes to 83.8. You get diminishing returns at 100, as you can see, but it's pretty good considering how little samples it needs to be retrained on in order to be applicable to a whole new data set. Okay, now that we've seen how schools and universities can sort of keep up with this, let's see how you can cheat better and try and fool these models again. So the defenders, the university and schools have gotten better. How can we cheat better? And the answer can surprise you with how simple it is. So this one right here that they're looking at is called changing the decoding strategy. Now, essentially, when a large language model is choosing the next word in the sentence, it does this based on probability. But how do you actually determine what your pool of words is going to be that you can draw from? So the main strategies here, I'm going to consider top P and top K because those are really the main ones. They've done other ones here, but it'll be a bit verbose and detailed to go into, and I'm not going to do it in my seminar tomorrow. So we'll skip over it and she'll be right. But essentially, top P is where you select a probability P, right? So like, for example, 0.8. And from the set of possible words that could come next in my sentence, I'm going to take the words that have a probability above P. So with this 0.8 here, I might have 150 words that have a greater than 80% probability to complete my sentence. Top K kind of flips that on its head. So you choose a number K and you select the K most probable items. So for example, here with 40, we're choosing the 40 most probable words, and then we're going to select from that to put into our sentence. So essentially, these models here are trained based on these top P, like baseline settings, right? So they're trained to detect large language models that have sort of got these parameters baked in. But what you can do if you're an attacker is you can change the parameters of your model. So instead of we're going to only accept the top 0.96, we're going to accept the top 0.8. That's a big difference. Like if your model is sort of doing this detection based on what words are likely to appear, then changing this like this completely widens your pool very, very much. And so it's no surprise that you get a significant change here, like the recall, I keep saying recoil, too much Counter-Strike, but the recall numbers here go down significantly for most of these except Fast. And we're going to get to that in a minute. If you remember, Fast was a little bit different from our other models here. And Top K is the same, but not as much. So it seems like Top P, if you change Top P decoding, it actually has a bigger impact than Top K, which is interesting. But this is just one method that they used, right? So you change the way that the probability of these words is generated. But as you can see, some of these still perform pretty well. In particular, Grover, Fast, and BERT Defense still perform pretty well. So there's probably more room for improvement here. They use some other methods as well. So one of these is priming the LM, which I'm not going to cover today because I'm not doing that in my seminar tomorrow. But a more interesting method that they've chosen is this one down here that's implemented in this table. So essentially, if your large language model uses some words more than others. So for example, let's say my large language model likes to use the word papaya a whole lot. I can see that if papaya is showing up in a lot of different places, then most likely that's going to be AI, right? That's how these ones here work because they're based on probability. But if I'm an attacker, I can notice that and I can say, okay, well, my large language model really likes to say papaya. So what if I go ahead and replace that word with a synonym? And that's essentially what they do here. So DFT Fooler and Text Fooler are two methods that they use to detect and replace synonyms that the defender's model is looking for. So yeah, let's say BERT Defense is looking for the word papaya. If I know that, I can swap papaya out for another word and it will fool BERT Defense and I'll essentially get around the AI detection a little bit better. Now, the way that these two achieve this is slightly different. So Text Fooler, the way this does it is it makes a lot of queries to the defender's model. And it's querying the defender's model to see what response it gets. And as it does that, it builds up a list of words that are important to the defender's model. Now, the obvious problem with this is that you're making queries to the defender's model. They're likely to notice if you make a whole bunch, right? So try doing that on Turnitin. Good luck, buddy. DFT Fooler is a little different. It essentially has a back-end language model that it uses as a sort of substitute. So instead of querying the defender's model, it queries this internal model. Now, the following dynamic gets sort of brought up here. Like Text Fooler, you can tailor make your evasion techniques to the defender's model. So if I'm trying to get around Turnitin, I just query it a whole bunch of times, find out what keywords it's looking for in what places, swap them out for synonyms, and I'm good. But DFT Fooler is going to be a little bit different. So I'm sort of like making my best guess as to what model they're using on the back end, and I can sort of sub that in and see what results I get. So you would assume that Text Fooler does really, really well, but the downside is they'll probably notice. Whereas DFT Fooler, you can just do at home, but you'll probably get varying results. So we can actually have a look at what this does basically. So with DFT Fooler, we've got this metric called evasion rate. So this is basically how many articles did we get through the filter. Now DFT Fooler, we'll go over Text Fooler first. Check this out. This is really, really good. As expected, Text Fooler has an evasion rate of a really, really high number because it can basically tailor make its evasion strategy to the model that the defender is using. Whereas DFT Fooler, you can see the results are a little spotty. You know, like it does really poorly on BERT Defense with the BERT backend. It does pretty well against GPT-2, and then it's sort of got mediocre results across the board. And then similar results with this GPT-2 XL one. It's maybe a little bit more balanced in the negative end, like in a bad way. But yeah, so another interesting metric here, by the way, is this GRN score, which is essentially a measure of linguistic quality of the text. Basically, the higher this score, the better. And what they're actually doing here is saying, before we made all of our swap out modifications with these two methods, we have a linguistic quality of this particular number. And after we make those sub-ins, we have a linguistic quality of this particular number. Now remember, if I'm a large language model, I want to maximize this number so that my text makes the most sense. But as you can see, the reduction it's somewhat marginal, right? Like it's okay, but for the evasion rates we get, it's actually like it's a decent trade-off. So you can sort of use this score as headroom basically for how much more you can mess with the text in order to try and fool something. Now the rest of this article is pretty much just yapping. It's not really that important for a high level understanding. They kind of just go into the finer details of, this is why this particular model was better. Like they sort of show the architecture of Fast down here, which is pretty interesting because Fast was the model that wasn't able to be fooled the most. It's the one that looks for semantic things in text, like locations, objects, people, etc. But yeah, the rest of it is kind of yapping, and I want to go over one more method of detecting AI cheaters that wasn't really mentioned in this paper. There's a really great video by Computerfile about it, actually. It's called Cheat GPT. And essentially the way that it works is if you can, it kind of flips this on its head because this article is looking at text after it's generated, whereas this other method is looking at text before it's generated, or while it's generating rather. So the essential idea behind it is at generation time, you can artificially modify the probability of certain words being selected, right? So the way that you do that is at every time you want to generate a token, you assign a red or green list to your complete set of tokens, sort of randomly. Like 50% of every word possible should be red and 50% should be green. And the ones that are red, you artificially lower the probability that those would show up in your output. So over an entire paragraph of text, you can say, okay, if more green words showed up than red words, this is guaranteed to be AI. And that ties in really interestingly with this paper's GLTR setup, because remember, these two models are trained based on probability. So essentially, we're just taking something that we already knew and making it more definitive. Like this can say, okay, yeah, based on the probabilities, this should be AI. But with the red green list, where you artificially lower the probability of those words, you ensure to like a ridiculously high probability that that text is AI generated. And because it's scattered throughout the entire text and it's randomized at generation time, it's really, really difficult for you to do a method like this one here, where they try and query the defender's model to change it, because there's nothing you can really do there. It's scattered throughout the whole thing and it's randomized each time. The problem with that is that you have to get large language model implementers like OpenAI and Meta to actually put that guardrail in. And we've pretty much seen that in the AI community, especially with AI images, if you put limitations on a model, either the community or another company will come in and jailbreak that model, or they'll just make their own new one. So the practical implementation of that particular strategy is leaves a little bit to be desired. And then also it's like, how do you retrieve the red-green list? Like if it's different each time, you'll need to retrieve the seed, right? How do you do that? It's not like when someone submits a cheated assignment, they're going to be like, okay, here you go, and here's the seed to generate the red-green list. They're just going to give you the text. So it's an interesting idea, but it leaves a little bit to be desired. I think this paper here is a much more practical way of like how to detect AI, and they provide some really interesting methods for how to get around it as well. So I thought it was a really good paper, well worth a read if you're interested. But yeah, hope you enjoyed.